Have you ever stopped to wonder how your phone or your smart speaker just gets you almost instantly? Well, today we're going to pull back the curtain on one of the cleverest tricks in the book. It's how computers process our language, not by reading everything word for word, but by thinking in chunks.
So let's just start right there with the big question. How on earth do they find answers so fast? I mean, you ask your phone something, and there's no time for it to sit back and ponder the deep grammatical structure of your sentence, right? It needs an answer, and it needs it now. So, what's the secret?
Well, here it is. They don't read like us at all. Instead of doing this deep, complicated analysis of every single word, they take a shortcut. And that shortcut is the absolute key to all the real-time responsive tech we can't live without. Okay, so let's get into what we're calling the language puzzle. You see, human language is messy, it's complex, it's beautiful, but for a computer, it's a nightmare. Trying to teach a machine to do a full grammatical breakdown for every sentence is just way too slow.
Just think about it for a second. A full grammatical analysis, what the pros call deep parsing, tries to create this giant, intricate family tree for every word in a sentence, showing how it relates to every other word. For deep linguistic research, that is super powerful stuff. But for your voice assistant trying to set a timer while you've got your hands full, it's complete computational overkill. It would just take forever. So to get around that speed problem, engineers came up with a really elegant solution. Instead of trying to understand the whole complicated tree, the computer learns to just think in chunks. And this is the big idea we're going to unpack today. So what exactly is chunking? It's basically the process of grouping words into meaningful little phrases, the chunks, things like noun phrases or verb phrases. But here's the most important part. It does this without building that big, slow, complicated grammatical tree. It's a faster, leaner way to get right to the meaning. All right, let's see this in action with a sentence you've probably heard 1,000 times. The quick, brown fox jumps over the lazy dog. To us, it's simple, but let's see how a computer using chunking would see it. Okay, first, the system scans the sentence, and it immediately spots a group of words that are acting like a single unit. It sees the quick brown fox, and it says, aha, that's a noun phrase. It just bundles them all together and treats them as one single concept, the thing doing the action. Next up, it finds the action word itself, jumps, and flags it. That becomes a verb phrase. So now we have our subject and we have our action, another essential chunk of meaning. And finally, it grabs over the lazy dog and groups that into a prepositional phrase, which tells us more about the action. And bam, just like that, instead of a complex tree, the sentence is now 3 simple, manageable chunks. The computer instantly knows who did what and where. Game-changingly fast. So you might be wondering, how does the machine actually learn to do this? It sounds like magic, but it's not. Let's take a quick peek under the hood at how this all works. Before any chunking can happen, there's a crucial first step called part-of-speech tagging, or POS tagging. This is where every single word gets a basic label. Fox gets tagged as a noun, quick as an adjective, jumps as a verb. You can think of these tags as the basic ingredients the computer needs to start cooking up chunks. So how does the machine use those tags to find the chunks? Well, a really common method is something called the BIO tagging scheme. It's actually pretty simple. The machine learns to label the beginning of a chunk, every word inside of a chunk, and any word that's outside of a chunk. It's a simple but really effective system for drawing those boundaries. Now, you might also hear people talk about shallow parsing. So what's the difference? Honestly, they're very similar. Think of shallow parsing as the general idea of finding phrase boundaries, and chunking as a very specific type of it that focuses on useful things like noun phrases and verb phrases. At the end of the day, they're both about one thing: speed over depth. Okay, so that's the techie stuff. But this is where it gets really cool. because this simple idea is the engine behind so much of the technology you use every single day. Let's look at a couple of real-world examples. First up, information extraction. Imagine a system reading a news headline. Using chunking, it instantly identifies the noun phrase CEO Tim Cook and the verb phrase announced new products. Right away, it can pull out a structured piece of data. This person performed this action. And this is happening millions of times a second across the entire internet. It's also absolutely critical for something called named entity recognition. When a system sees a sentence like this, chunking helps it immediately spot Apple Inc. as a single unit, a single noun phrase. This makes it way easier for the system to then go, oh, that chunk is an organization. This is huge for search engines, for data analysis, for everything. So if you boil it all down, chunking gives us three massive benefits. First, it is ridiculously fast, which makes real-time apps possible. Second, it cuts through the noise by focusing on whole phrases instead of getting lost in single words. And third, it's a vital first step that makes more complex language tasks easier and a whole lot more accurate. But, it's not a perfect system. Of course not. This shortcut approach has its limits, and researchers are working hard every day on the challenges that are still on the road ahead for true machine understanding. Our language is just plain tricky. Take a word like book. Am I talking about something you read, or am I about to book a flight? That ambiguity can trip a system up. You can also have phrases hidden inside other phrases, which gets complicated. And of course, the rules that work for English might be totally useless for Japanese or Arabic. And a big one, if that first step, the POS tagging, gets something wrong, well, that error just snowballs from there. But even with all those challenges, this core idea is still incredibly important. It really boils down to this. These techniques are powerful, fundamental tools that help machines build a bridge across that huge gap, the gap between just seeing a bunch of words and actually grasping what they mean. Which kind of leaves us with one last big, fascinating question to think about. By taking this shortcut, by breaking our beautiful, complex language into these neat little pieces, are machines truly on a path to understanding us the way we understand each other? Or are they just getting better and better at a very, very clever imitation?